I'm going to talk about rifting and rheological heterogeneity, looking at zones kind of building on what Andre just presented, so from fault damage zones all the way to kind of plate boundaries. Okay, so yeah, just a big thanks to a lot of collaborators on this work, so in particular Juliet Biggs, who is my postdoc advisor, but also Jack Williams and Ake Fagareng at Cardiff and Hassan Dala at the Geological Survey Department in Malawi. Okay, so I'm going to start by just talking about the kind of motivation for this study. And really it's considering the driving forces of continental extension and the strength of the lithosphere. So we know that the plate mantle system is driven by gravity and resisted by the strength of the mantle and the crust. And we have really good kind of knowledge of the sources of buoyancy within the mantle, things like slab push and pull, mantle upwelling. But really the strength and rheology of rocks as a pressure, function and temperature are really comparatively poorly known. And as a consequence, we can't even solve one side of this kind of equation I've shown at the top here. We also can't really know all the driving forces because of the intralithospheric heterogeneity, which plays an important role in driving continental extension as well. And that's what's kind of formed this plate force paradox. It's quite a sort of old problem now, but essentially the tectonic driving forces are insufficient to rupture thick, cold continental lithosphere. Okay, so a few years ago, there was kind of a big explosion into looking at magmatic rifting, and that was kind of seen to solve this kind of rift force paradox. But we know that a lot of the regions have very, very low magmatic input or even no magmatic input. And it's actually very, very difficult to make these measurements of lithospheric strength and rheology. So instead, what I'm going to use is these kind of results from some numerical modeling, which shows that rheology has a fundamental impact on patterns of deformation at the surface. So here's a nice example here from a paper published in 2019, which shows, if you have a very strong crust, you have very, very narrow asymmetric rifting, all the way to potentially a weak crust and wide rifting with strong decoupling at the base of the crust. So I'm going to use this and actually use patterns of deformation at the surface to make some inferences about the rheology of the lithosphere. And I'm going to follow on quite nicely from Andre's talk by talking about amagmatic rifting along the East African rift and particularly focusing on Malawi and the southwestern branch of the East African rift. So in this region, the lithosphere is very thick. It's over 150 kilometers. It's pretty old and cold. And the whole of the crust, which is about 40 kilometers thick, is seismogenic. So Andre showed the earthquakes there occurring down to 30 kilometers depth. The rifting is largely amagmatic, and the initial stages of rifting are thought to be accommodated on large offset border faults with any displacement in the interior of the rifts caused by flexure. And kind of existing attempts to understand the rheology of the lithosphere in this region are incompatible with research. So if we have a felsic lower crust, it's quite difficult to initiate earthquakes greater than 30 kilometers depth. But if you put in place a mafic lower crust, it's incompatible with seismic observations of crustal composition. So what I'm going to do is to look at three different scales, really. So going from continental scale deformation and plate models, all the way through individual rift basins and through to deformation within individual fault damage zones to examine the strength of the lithosphere in southern Africa. So starting off at the plate scale. So this is an image on the right-hand side of the African plate, or the Nubian plate, and the sort of splitting up of the continent of Africa into a series of smaller microplates. But you can see with these little small circles and the focal mechanisms plotted here that a lot of the seismicity is actually occurring away from these plate boundaries. And in particular, there's also a line of active fault which runs kind of along here through Zambia and into the Okavango Rift, which aren't accounted for by the existing plate models. So what we did was to install new GPS data, principally in southern Malawi, and to explore whether the Nubian plate here is acting as a rigid tectonic plate, or whether we can model this with a different plate configuration to that currently shown. Okay, so to do that, we use the GPS, so including the new GPS stations we installed in Malawi, but also existing stations in Africa. And we do a statistical test as to whether this Nubian plate can be split into two along the boundary which runs from the top of Malawi, through Zambia and into the Okavango Rift. So to do that, we take these GPS stations, we calculate the chi-squared value of the existing plate configuration, that's shown as 115 here. And then we repeat that exercise, but when we split the Nubian plate into a separate plate, which we called SAN here, and you can see there that the chi-square value is decreased, and we can actually calculate whether the reduction in chi-squared is statistically significant using an F test, and we found that it is at 99% confidence interval. So essentially, this SAN plate here is acting as a distinct tectonic plate from Nubia, and is moving independently. So now if we plot that boundary of the SAN plate alongside the cratonic regions in Africa, and what we find is this correspondence between the edges of the cratons and this new plate boundary. And that holds for some of the existing plate boundary, in particular here with the sort of Ugandan rift and the southern end of the eastern branch of the East African rift. So these boundaries bear a very close resemblance to the edge of the Archean cratons in southern Africa. And so these cratons are comparatively rigid compared to the surrounding metamorphic belts. And so what we suggest is that it's the compositional differences between the cratons and the metamorphic belts which are actually driving strain localization at the edges of the cratons. So next I'm going to zoom into Malawi and focus on this region, looking at more rift scales of deformation. So I'm going to particularly focus on southern Malawi. So this is Lake Malawi, the southern end of Lake Malawi, just at the top here. This is the capital of Malawi, Lilongwe. And really, before we started this project, we really only had knowledge of one active fault in this region. This is the Belina Mataka fault. It's an amazing 100-kilometer long normal fault. It's got a 15-meter high scarp. And in 1997, Jackson and Blenkinsop kind of suggested that it might have been possible to host a magnitude 8 earthquake on this fault. So there's only 2 GPS recording stations prior to our study, no seismic stations, and the only real earthquake that was known about was that magnitude 6.1 earthquake that occurred that Andre was talking about in the previous talk, down at 32 kilometers depth. And that was just at the northern end of the Belina Mataka fault, just up here. Okay, so following this, we now know about 14 active faults in this region. We've observed recent lake quaternary activity, both in the field and using high-resolution topography, and there's a series of papers you can read to find more about that. We find evidence for multiple magnitude 7 earthquakes on the faults, which range in length between 50 and 100 kilometers long, and again, some more publications. And we have now a network of 14 GPS stations, and that paper I've just talked about is published in GRL just this year. And we've incorporated these into active fault databases and seismic hazard assessment. And there's a paper here by Jack Williams, but there's a couple more papers coming out in the next few months. And Jack actually gave one of the Rifted Margins talks earlier this year on that as well. Okay, so I'm just going to talk about one particular individual graben in that rift system in southern Malawi, and that is the Zomba Graben. So this is a 50-kilometer wide graben in southern Malawi where we mapped 5 active faults using the Tandem X data. And what we find is clear evidence for lake quaternary deformation, fault scarps that offset both alluvial fan sediments at the edge of the rift and paleo lake sediments within the interior of the graben. And you can see here, this is a nice example of an offset alluvial fan. It's been displaced vertically by about 30 meters in this case. Here's another nice fieldwork photos, this time from a drone. This is the photo I showed on the front cover. This is a fault known as the Mulungusi fault. It's right on the interior of this basin. In the field, we're able to find a really clear 6-meter high fault scarp, and that was echoed in our observations from high resolution topography as well. And again, another example, and this topographic data that we use is great because we can actually tease out kind of multiple generations of slip. So on this quaternary fault scarp, you can see a total of 18 meters of displacement, but there's a more recent generation of scarps which are just 9 meters high. So we mapped each of those 5 faults, and using the high resolution DEM, we could actually observe the fault scarps which range along each of those faults, which range in height from between 5 and 30 meters high. You can see here that this is one particular fault where we have an up to 30-meter high scarp. And what we did using those measurements of scarp height was actually calculate the strain across each of those faults in boxes, approximately the length of the graben, and that's using a Kostrov summation. And that's shown in the bottom image here. So each of these 5 kilometer widths, we calculated the strain in that. And you can see that actually the strain in this region is not just dominated by displacement across the border faults, but actually approximately 55% of the strain is occurring on the intrabasinal faults, in particular this one intrabasinal fault here.
Look, you're 10 minutes now.
Great, not too long to go. Okay, so why is it this deformation distributed in the Zomba Graben? Why is it distributed within the intra-rift faults? Well, one idea could be that the current distribution of strain represents a period of time prior to localization of strain across rift border faults. Well, we don't think that's the case because we have this large border fault, topographic signature of this border fault you can see in this elevation plot here. So what we think might be happening is that the intra-rift faulting continues after a period of strain localization across the rift border faults. Now, I said earlier that this was typically thought to be caused by flexure in these regions, but this requires quite large offsets on the rift border faults, many kilometers of displacement, which was simply not present in this region. So could it be fluids? Well, we know that magmatic fluids and volatiles facilitate extension across much lower stresses. But beneath Malawi, there's no evidence for active magmatism. But we can't rule out decompression melting or some sort of lower magmatic intrusion, which might not lead to kind of effects at the surface. But what we really think is happening is that there's some lateral heterogeneity within the lower crust, which would enable relatively distributed deformation within a narrow rift in an otherwise quite strong lithosphere. And it doesn't require pre-existing frictional weaknesses, which we know from Andre's talk, for example, don't exist in this region. Okay, and then finally, I'm going to focus in on individual fault damage zones. So this is an image from a fault damage zone across the Tiolo fault in southern Malawi. And we're going to look at both macro and micro scale observations. And this is about 50 meters from A to this edge of this space of this fault scarp here. And when we look at the macro scale damage, we see that at the edge of this fault zone, the rock is cohesive, so it's not damaged at all. This pegmatite vein, for example, has not been offset. As we get closer to the fault scarp, we see increasing levels of macro scale damage and some minor slip surfaces. We also see that same pattern echoed in the microscale fracture density. So fractures within this quartz and feldspar range, you can see that increases as we get close to the fault scarp. There's only within this zone around about 50 meters wide in the footwall here. Okay, so to summarize what we saw on that fault, we found a very narrow fault damage zone, which is associated, we think, with quite localized strain, both at the surface, but also at depth within a narrow shear zone. And the effect of that increased strain rate within a narrow shear zone has the effect of potentially increasing the brittle-ductile transition depth and allowing earthquakes to occur at much greater depths than we possibly think at the moment. So just to summarize now, so using high-resolution topographic analysis, field observations, and GPS data, I've shown that there's a new statistically distinct plate in southern Africa with a boundary along the southwestern branch of the East African rift system. We find evidence for active fault scarps across this Zomba Graben in southern Malawi, with strain across the intra-rift faults much higher than previous models have suggested. And we find that for the fault zones in southern Malawi are very, very narrow given the amount of displacement we've recorded across these faults. And the implications for the rheology of southern Africa is that strain is concentrated in regions around the Archean cratons. Lateral heterogeneity within the lower crust enables distributed strain within individual rift basins. And narrow fault zones are probably promoting higher strain rate within individual fault zones. And yeah, that's it. Thanks very much for listening.
Thank you, Luke. You managed to really fit 3 different studies into one talk. Okay, there's time for a few questions. Type them in the chat or just a queue, or raise your hand if you want to ask one. While you are typing, I ask my question. So you said that this third mechanism, that there's intrinsic heterogeneity that makes these intra-rift faults being alive at an early stage. What does it mean for other rifts? Is there a different type of heterogeneity if they don't exist there? I'm thinking of maybe somewhere further north in Kenya or so. Or is that something that you would think happens all the time and we just don't see them anymore?
Yeah, that's a great question. And I don't necessarily know the answer. I guess this is a call that we need probably more observations of those early stages if we can. Especially in regions with very strong lithosphere. So I know that Donna Shillington has had some sort of similar result in the North Basin of Lake Malawi. So she published a paper which, both our papers came out in the same edition of Tectonics in 2020, kind of showing the same thing, that actually quite early on in the sort of rifting process in this thick lithosphere, you actually get more distributed deformation than we perhaps previously thought. I know if you look at like Patience Cowie's models, for example, they always start with distributed deformation. And so my suspicion is that we just never really spotted that. We don't have the temporal resolution in a lot of the seismic data, which kind of inform the models of most of our models of rifting. But, I guess it's for, us people that do active tectonics to go out and try and find these regions and maybe show the existence of this kind of more cryptic phase in better detail in the future.
Could you imagine that also the rift velocity plays a role? Because all these examples that you mentioned, they take place in really super low velocity rifts. Maybe the border fault is healing to some degree at these low velocities?
Yes, possibly. Although the thing with the Malawian rift is that the fluid flow is very low. So it's a very, very dry crust as well. It's been through lots of phases of metamorphic deformation. So there's no reason that we think there's particularly kind of enhanced fault healing in between these during this phase. So I'm sure rift velocity would play a part, but I also think the composition of the crust and the sort of moist, the fluid content within the crust would make a difference to that as well.
Mm-hmm. Okay. Suzanne has a question.
Yes, right. Thanks, Luke, for your talk, first of all. And it's a bit about the rheological implications what you have up here. So I can sort of see your argument for that the heterogeneity might make the strain more distributed, right? But it does mean that the heterogeneity then has it must change the rheology somehow or other to do that. Say from the Malcolm models, we find that if there's less strength contrast with depth, then you tend to be really find where to localize. It goes more towards pure shear almost, right? But then caught up by many more faults. So could you speculate what the lateral heterogeneity in the lower crust, what that could be, so that it would contribute to more distributed deformation?
Yeah, I mean, so I lost your question in the middle there, but I think I understood most of what you were saying. So, I mean, I think in the paper we suggested there might be some sort of anastomosing shear zone. So you have, these regions of intact, kind of quite strong lithosphere or crust left, but you may have some kind of weaker zones kind of interweaving with this, which would kind of reduce the strength in quite a limited zone. So you might not see it that in the sort of bulk rheology of the whole rift, as it were. I mean, yeah, what do you think about that?
Yeah, I mean, one thing I find, admittedly very simple experiments is if I put a lot of pre-existing like shear zones, positive thick shear zones, right? And then I load the system, that many of these, depending on the rheology, many of these pre-existing shear zones would just be ignored because the system wants to localize. Right. So giving it the opportunity doesn't always mean that it really does the localization. There has to be more to the overall system to make it distributed.
Yeah. Okay.
So your observation is very, very interesting here.
Yeah, I mean, I guess I can't answer your question, but maybe there has been some recent seismic observations that suggest there might be some in the very base of the lower crust, some kind of I guess it's a much weaker lower crust than perhaps we previously assumed. So would that sort of thing do it? If you combine the heterogeneity with the weaker lower?
I mean, I find that if you make the lower crust weaker, I mean, it depends on many things. But if you have a very simple system and you have more strength contrast, then it would localize more.
Okay.
All right. But it depends where you are in the rifting system. But that would apply to, say, the continental states which you have here. Whereas if you would go to, say, more the rifted margin mature states, like the models that Sasha has been running, you could make a very wide margin when you have more of a weaker lower crust. Yeah, so there's no straightforward answer, even not from the models, and so the observations are very interesting.
Yeah, well, yeah, I agree.
Give us some clue, I think not so what yet, but
when we wrote that paper, we struggled to explain it with kind of most of the existing kind of modelling papers, and it was quite heartening that Donna's paper that came out at the same time kind of confirmed our observations. So maybe this is a call for you guys to explore this.
thanks.